Hello, scholars, and welcome to our lesson on proving and using similar figures in problems. This is in Transformations and Volumes, and it is part 1. You'll use what we have learned about similar figures and dilations to prove shapes similar and find missing sides of shapes. The reason we're doing this is because, as discussed previously, geometry quite literally helps to shape the world we live in. Because we live in this world, it's best that we know how to use methods to move and change shapes, or in this case, identify if shapes were changed properly and find missing sides of shapes. Let's begin. First, with a warm up pop up. Oliver was enlarging and printing some images for his classroom, but some of the images looked like they weren't enlarged right. Which ones does he need to reprint? Let's see it go through. So, which of these images, which ones need to be reprinted? All right, doing a check-in. You might have noticed right away, especially if you're more visually inclined, that it looks like our mushroom and our little hat here, they are definitely squished. The mushroom looks like it's got way more narrow, and the hat looks like it got squished way down. The wand looks okay, though. If you also recognize which ones need to be fixed, the mushroom and the hat, then you were absolutely correct. Identified which ones didn't get enlarged correctly. Because remember, an enlargement, the shape shouldn't actually change what the actual shape looks like. It should just get bigger or smaller. Let's clear this up and go to the focus, which is first, proving figures are similar. If we are shown shapes and want to know if they are similar figures, there are two methods we can use. One uses angles and the other uses sides. First, let's go with similar angles. Two shapes have congruent corresponding angles. Congruent, remember, means the same. So if we have two triangles here and we're asking, were these actually reduced properly or enlarged properly? If we know that they both have 60 degrees there, 65 there, and 55 there, if all their angles are the exact same in the exact same places, they are similar figures, meaning that they were dilated properly. We also have the similar side method. One shape's sides can be found using the same scale factor on the other shape's corresponding sides. So we have 2, 3, 3, and 4. So in this case, you might already see, to turn 2 into 4, you could double it. 3 into 6 could be doubled, 4 into 8 could be doubled, meaning they all use a scale factor of 2 to get to the other shape. Because they all use a scale factor of 2, we could do times 2 times 2 times 2 times 2 to get these sides. That means that these are similar figures. Now let's use a side theory to answer a question. Are the shapes below similar figures? Explain how you know they are or are not. So our shapes here. Step 1. This is where we have a choice. When we're doing things like finding scale factor, we don't have a choice in this, but when we're just proving that shapes are similar, we can decide which one we want to be the new and which one is the original. As it says, because we're going to be doing some division, it may be easier to choose the larger shape as the new. And I will do that. We're going to say that the smaller shape will be our original, and our bigger shape will be our new. So that was step 1. We've now determined what's our new, what's our original. Step 2. Find the scale factor of each corresponding side pair by dividing the new side by its original. So we have 4 side pairs, so I'm going to do this 4 times in a row. Let's see here, I'll get my colors back out. So for new, we have 8 right here. We have 10 right here. And then we have 8 and 10 again. So 8, 10, 8, 10. We're going to be doing a whole bunch of division here. So division, 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 division of the new. So we did 8, 10, 8, 10. We're going to do 3, 4, 3, 4. 3, 4, 3, 4. So I do need to do that division now. Let's see here. If we do 8 divided by 3, which will actually, in this case, answer 2 of our division questions, because we have a lot of matching pairs here. 8 divided by 3, it gets me 2 point, it's actually a repeating decimal. 2.66666 going on forever. So I'll put just 2.6 repeating. Let's see about 10 divided by 4. 10 divided by 4, I get 2.5. Once again, 8 divided by 3, I get 2.6 repeating. And 10 divided by 4, I again get 2.5. Let's go to the last step now that we've done our division. The last step is, if the scale factor is the same for each side pair, it is similar. Well, if we want to check our pairs here, we have 2.6 repeating. Oh, then we have 2.5. That's not the same scale factor. That means these have not been scaled up correctly. So if they're asking, are these similar figures? We're going to say, no, they're not. We're going to say, they are not similar figures. Again, for them to be the same, it means that I almost ran an R there. For them to be the same would mean that I should have gotten 2.6 every single time or 2.5 every single time. I did not, so they are not similar figures. Make sure you get your notes in, but I'm going to clear up and go to the UTRA. So it's time to see what you know so far. Pause the video to try this problem on your own and resume when you are ready to check your answer. All right, are the shapes below similar figures? Explain how you know they are or are not. All right, doing a check-in, of course. Pause if you've not finished. As we mentioned before, it might always be best to treat your biggest shape as the new and your smaller one as the original. Once again, you don't have to do it that way. You could choose the other way. The biggest thing is, though, you need to choose one way and stick with it. Because if we do 12 divided by 4 the first time, but then do 5 divided by 15, you've mixed it up. You always need to do one side divided by the other. With that, you would then be gathering up all your sides. For new, we have 12, 15, and 18. So that's 12, 15, and 18. For the news, and make sure you're doing the matching ones. I did 12, 15, and 18, so I'm doing 4, 5, and 6. 4, 5, and 6. And all of that is getting divided. If you set yours up correctly, the same as well, you're doing good so far. Lastly, if we do 12 divided by 4, you would have gone 3. If you do 15 divided by 5, you would have gone 3. And if you do 18 divided by 6, well, you would have gone 3. So if you notice that all 3 had the exact same scale factor, so you said they are similar figures, then I would say that you were absolutely correct. Now, they do say to explain. You could just say because they have the same scale factor. Because they have the same scale factor. So if you also determined that they were similar figures, you were absolutely correct. If you went a bit awry, as I said, one way you could mess up is by mixing up which side you're dividing which side by. Or you could have mixed up that you weren't using matching corresponding sides. Like the bottom needs to be divided by the bottom, the right side by the right side, the left side by the left side. With that, I'm going to clear this up and go to the closing. So we can prove shapes similar by checking if each corresponding side was scaled up or down using the same scale factor. That's what we focus on this time. With that, I will be seeing you in part 2 of this lesson in a moment.